Well, Bracken Cave Preserve is owned and protected by Bat Conservation International. The cave itself is about 650 feet long. It's 100 feet wide at the floor and 117 feet floor to ceiling. So you have this large cavernous space that's under the ground that's full of millions and millions of bats. So the environment inside the cave is unlike most caves in this area. My hobby's caving, so I spend a lot of time in caves, crawling around under the ground. But Bracken, because of all the millions of bats that are living in the cave, and they generate a lot of body heat, and there's lots of guano in the cave. The guano is anywhere from 30 to 60 feet deep. So the combination of all these millions of bats and the decomposing guano generates a lot of heat. So temperatures inside the cave are 102 to 104 degrees. So it's very hot in the cave. It's very humid. The guano, again, is anywhere from 30 to 60 feet deep. So you're walking through, in some places you might be knee deep in guano. And then the floor of the cave is covered with domestic flesh-eating beetles. And so literally the floor is alive and moving. And the beetles eat any bats that fall on the floor, and they eat the bat guano, and they're basically the housekeeping crew. They keep the floor of the cave clean of bats. So it's a pretty extreme environment in there with temperatures. You have flesh-eating beetles. The air in the cave, as you can imagine, with all the peeing and pooping that the bats are doing, the temperatures and the ammonia levels are very high. There's lots, because of all the exhaling of the bats, the CO2 levels are very high in the cave. So those, you have poisonous gases, and you have low areas that you're not very much oxygen. So it's a pretty extreme, harsh environment to be in. So we have to wear protective gear when we're in the cave so that we can breathe, and the ammonia won't kill us.
What we're doing here is what's known as an electrical resistivity experiment. And what that involves is putting electrical current into the ground through all of these metal stakes. Most of them are buried all the way up to the hilt. And then measuring the amount of resistance between one electrode to the other. So the ones that are close together, the current will go a little ways into the ground, and it will tell you what's going on there. The ones that are far apart, the current will go a deeper route into the ground, and so it sends current. All this equipment basically sends current through a combination of electrodes to measure shallow and deep depths. The computer merges the data and then gives you a result. Every type of material has different properties in terms of how it conducts electricity. Some conducts it very efficiently, some very poorly. And so what we're looking at is the contrast, the differences between the materials. So in this case, what I'm expecting is that the bat guano will have fairly low resistance, especially the deeply buried stuff. It'll become kind of like a clay, that'll hold some moisture, and of course, wet materials tend to conduct electricity a little bit better than dry materials. And below this floor, we know that this part of the cave formed by collapsing into a deeper part of the cave. And so there'll be a rubble pile below this. And so that rubble, the limestone, is going to be more resistant to the current. And of course, there's going to be gaps, air pockets in there. And air basically has near infinite resistance. So that will have a higher resistance than the guano. So I'm looking at the difference between the two. Now, the technology has been around for a long time. The first time I did this was back, I think, 1977, where we basically hammered, a little electrode into the ground and hammered another one and touched wires together, and we read the resistance on a meter and wrote the numbers down. and then pull the electrode out, hammer it into the ground somewhere else, measure the distance, touch the wires together. Computers make life so much easier because now we just put in this case 56 electrodes. We connect this cable that has all sorts of little wires in it, and then that just sends the signals back and forth, and then it processes, it does all the math, and then gives us beautiful results. And it can run tests, it can run many iterations of the data until it finds the optimal processing. Now in the cave, what I'm doing right now is just a rough cut of the data processing. You know, to be more efficient with our time here, I'm looking at what the data look like just roughly. When we get it back to the office, we can process it a little bit more. There's some bad data points that we'll throw out. These always occur. Also, we'll end up putting in some corrections where we're going to survey this line and adjust for the fact that some electrodes are higher than others, because that will have an effect on how current moves through the ground as well, and that will change the picture of what we're seeing down below. Well, what's happening is BCI, Bat Conservation International, contacted my institute, the National Cave and Karst Research Institute, to assist with this project. And the ultimate goal is to pull out some cores of the bat guano to do paleoclimatic and paleobiological studies of the cave. The question is, where do you put in the core? You know, where do you dig? You know, do you dig down here and you only get a foot down, or do you dig over there and get 20 or 30 feet down for a longer core? And so this is the first step in that process. We're going to do 3 surveys in this part of the cave, and then we've got an area back there at the very back where we're going to do a 3D survey. Here I'm expecting that the deep areas will be these narrow sections where a 3D survey really would be overkill. But then we'll process the data, we'll say these are the deep spots, and we'll leave the little pin flags in place with the numbers, and I'll tell BCI go to 1-52, because that seems to be the deepest spot, and that's where they'll pull the core out. Then the other 2 partners involved with this they'll pull out the core, they'll do the analyses, they'll look at carbon-14, oxygen isotopes, carbon isotopes. We've got some paleontologists who will look at bat bones, because we expect there's going to be a lot of bat bones down here in the guano. And the bat bones will tell them, has it always been the same bat species? Has that changed over time? Were they here now, gone in, 1,000 years ago, let's say, but then here 5,000 years ago? We don't know. And so this will help give us some of that information. So the fundamental part, of course, is the age dating, because we can observe changes, but if we don't know the ages to correlate to, then we really don't know nearly as much. So that's the ultimate goal, is to get a better handle on what's going on here. The biologists also can look at the guano itself, because currently the bats in the cave are insectivorous. They eat flying bugs. And the hard chitinous exoskeletons of the bugs basically pass through their gut, and they come out broken up, but often identifiable. And so right now we know that the Mexican freetails that live here in the cave primarily eat moths. That's their big juicy steak. People worry about mosquitoes. Yeah, they eat mosquitoes, but those are like potato chips. Not a whole lot of nutritional value, but moths are the real big things. Well, maybe that changed 1,000 years ago, or 5,000 or 10,000 years ago. We don't know how far we'll see into the past, because it depends on how deep we can see and sample the guano. There is this idea that you have to have a clear, well-defined purpose to go out and do science, in the sense of the immediate benefits to humanity. And in this case, it gives us a better understanding of the cave, the work we're doing. It doesn't give us, at least in my mind, an immediate conservation benefit. But there is so much in science that we've learned by accident, or that you may have collected some data 50 years ago that he then figured out was really important, where you just missed it, you know? Or maybe you didn't have the technology or the other information to really make the connection. And so this gives us a better understanding of the cave, of the climate, of how things have changed. If we understand what's in the guano, we understand what was on the surface. If we want to talk about how climate has changed, well, here we've got a picture of what the climate was like in this spot 1,000, 5,000, however many thousands or hundreds of years ago. There is tremendous work going on in climate science. And one of the things that's being recognized by scientists around the world is that your best paleoclimatic information is to be found in caves. There's been tremendous work done by coring the ice sheets in Greenland and Antarctica. There's been tremendous work studying deep sea core data. And that's great stuff. I mean, I'm not going to take anything away from it. But what it does is it's telling you what's going on in Greenland and Antarctica and somewhere in the middle of the ocean. You know, and then you have to interpolate what it means in terms of here in Central Texas or whatever part, you know, of the continent you have to be living on. But with cave data, what you have is here is what happened right here in this spot precisely at this time in the past. And it's a richness of information. So for instance, with the guano, we can look at carbon, we can look at bugs, we can look at bat populations, but in other caves, we can look at cave sediments and see what's washed in, pollen, spores, what sort of plant communities were on the surface. There's a lot of study looking at stalactites and stalagmites in caves, looking at oxygen isotopes and other information that tell you what the temperature was like outside. You know, I mean, there's just incredible richness of data. And rather than just, again, interpolating it from some great distance, we can have thousands of data points on the continents wherever you have caves to really say what was going on there. So climate change really is a big conservation issue right now.